Hi everyone, thank you for watching our presentation on efficient contextual representation learning with continuous outputs. I'm Harold at UCLA, and the work is jointly done with Patrick Chen, Charlie Hsieh, and Kai-Wei Chang. Contextual representations, such as Elmo and BERT, have become the backbone of many NLP models. However, training them is known to be a resource-hungry process. For example, even Elmo, the current smallest contextual representation, takes about 2 weeks to train using 3 GPUs and produce a large amount of carbon dioxide. There have been rising concerns about the energy implications of NLP models. As shown in the graph, finished tuning and experimentation of a simple NLP model may produce 2 times more carbon dioxide than an American in 1 year. So in this work, we aim to accelerate contextual representation learning. Contextual representation models are pre-trained language models. They first project each word of the input sentence into embeddings through an input layer, using either subword embeddings or a character CNN. Then the sequence of embeddings is passed through a sequence encoder, such as an LSTM or a transformer. Then the output vector from the sequence encoder is passed through a softmax layer, creating a distribution over the vocabulary. The model is trained using a language model objective. Given that the work was developed in late 2018, experiments are conducted using Elmo. So in later parts, we will center our discussion around Elmo. However, the method is also applicable to other models and deliver considerable speedup. To accelerate the training process, we argue that the softmax layer is a primary cause of inefficiency. Specifically, the sequence encoder output a context vector C of size m. C is multiplied with W, a matrix of size V by m, with V being the vocabulary size. Then a softmax function is applied to create a categorical distribution over the vocabulary. When training on very large corpora, they could become very large. For example, for Elmo trained on the 1 billion word corpus, the vocabulary size is 800,000. The resulted matrix W takes up 80% of all parameters of Elmo. In such case, the softmax layer becomes a speed bottleneck. Thus, instead of using the softmax layer, we use a continuous output layer. Assuming that we have access to a pre-trained word embedding for words in the vocabulary, the continuous output layer directly minimizes the distance between the context vector C and the pre-trained embedding of the target word W. The distance function could be L2 distance, cosine distance, or more sophisticated functions. In this work, for simplicity, we use the cosine distance. Essentially, we're predicting the word embedding instead of the word. This approach was proposed by Kuma and Svetkov and used for machine translation. We're the first to test the continuous output layer for contextualized representation learning. The benefit is evident. This approach reduces the time complexity of the last layer from the size of the vocabulary to the size of the embedding vector. The time spent on the output layer now is almost negligible. It also greatly reduces the trainable parameter size of the last layer from tens or hundreds of millions to 0. In the case of Elmo, that is 80% total parameter reduction. Various solutions to the large vocabulary issue have been proposed. For instance, we can sample part of the vocabulary when doing softmax. The adaptive softmax reduces computational cost by allocating less resource to rare words, while the subword method keeps a small vocabulary by splitting up rare words. However, the continuous output layer is more efficient than all these methods. This also brings efficiency improvement for the whole training process. With less trainable parameters comes less optimizer overhead. We're also able to improve the GPU memory efficiency and fit more words per batch. The communication cost for multi-GPU training, which is proportional to the trainable parameter size, is also drastically reduced. In practice, while Elmo took 14 days to train on 3 GPUs, we can train a comparable model in 2.5 days on 4 GPUs. When using the continuous output layer, we assume access to a pre-trained word embedding. What if the target word is not in the vocabulary of the pre-trained embedding? We resort to open vocabulary word embeddings, such as fast text and mimic. They use subword or character level information to provide embedding for novel words. With such technique, we can essentially train our language model without truncating our vocabulary, as we can calculate word embeddings for novel words on the fly. Thus, we introduce our model, ELMO-C, which means Elmo with continuous output layer. We use fast text embedding trained on Common Crow as a pre-trained word embedding, which we denote as fast text CC. In addition to replacing the Softmax layer, we made a few slight changes to Elmo that we find beneficial. First, the original Elmo has CNN as the input layer, and for computational efficiency, we use the aforementioned fast text embedding as our input layer. We also add layer normalization between LSTM layers. To make a fair comparison, we introduce two additional baselines, Elmo A, which means Elmo with adaptive softmax, and Elmo sub, which means Elmo with subwords. Adaptive softmax and the subword both are popular methods for dealing with a large vocabulary. All models are trained on the same corpus for 10 epochs, following Elmo. The two baselines, Elmo A and Elmo sub, are trained with the exact same hyperparameters as our Elmo C. We especially note that Elmo A, Elmo with adaptive softmax, achieves a perplexity of 35.8, lower than 39.7 of the original Elmo. This indicates that the introduced baseline is strong and fair. First, we want to compare the computational efficiency of the models. In the table, we report the whole training time, the batch size per GPU, and the trainable parameter size. Comparing Elmo and our model, Elmo C is 4.2 times faster and 6 times more memory efficient. We also see a significant reduction of trainable parameter size. Elmo A and Elmo sub are more efficient than Elmo, but our Elmo C is still 1.6 times to 2.3 times faster. Being drastically faster, we test whether the model's performance will degrade as contextualized representations. Thus, we transfer the trained Elmo embeddings to downstream tasks and compare the performance. We follow the setting of the original Elmo and test on 5 NLP tasks: SNLI, CAREF, SST5, NER, and SRL. We find that Elmo C is comparable to Elmo on 4 of them, except on SRL. The slightly inferior performance on SRL is partially due to the input embedding we used, and please refer to the paper for detailed analysis. Compared to Elmo A and Elmo sub, our model rivals or outperforms both. Thus, we conclude that the continuous output layer, when applied to Elmo, delivers significant computational benefit without degrading the transfer performance. The presented approach can accelerate the last layer of the model significantly. However, as the rest part of the model, such as a sequence encoder, grows larger and larger, the speed bottleneck might no longer be the softmax layer, and the overall speedup we enjoy might shrink. Thus, we empirically test for sequence encoders of different type and size how much computational benefit the continuous layer can bring to the entire training process. We test LSTM with the same hidden size as Elmo, and a two-layer LSTM, also same hidden size as Elmo, and also transformer base large, as in the original transformer paper, and GPT-1, which is the same size as bird base. We compare with the subword approach, the adaptive softmax and the sample softmax. We report not the speedup of the last layer, but the speedup of the entire model, and find that our approach can achieve 1.4 times to 8.3 times overall speedup. In conclusion, we find that predicting the word embedding instead of doing softmax accelerates Elmo training. The resulting model Elmo C retains comparable performance as Elmo. We also show that the computational efficiency sustains when the technique is applied to large transformers. Our code is available on GitHub. Thank you for watching.